Good morning, class. Today we're going to start a new set of notes. We had already looked at electrostatics back in February when it was nice and cold and dry and we could get good static charge built up on stuff. Well, today we're going to look not at static static charge at rest on the surfaces of objects. We're going to look at what happens when charge transfers through a conductor, what makes it do that, and how we measure it. So we're going to be talking about electric current, and then we'll go into a little discussion about electric power as well. So in order to get electric charge to move through conductors, there has to be something that does work to move each charge. That something is called a potential difference. Potential difference is denoted with a capital V, and that's how I make my capital V to distinguish it from a lowercase v. And it's measured in a unit called a volt. Now, which is indicated with a little v. So big V is indicated with little v, if you want to look at it that way. They go together. Now, potential difference, or voltage as you might hear it called sometimes, is what actually pushes the current through the conductor. It does the work on each charge to move it from high potential to low potential. Very similar to what gravity does. Gravity accelerates objects from a high gravitational potential energy to a low gravitational potential energy. Well, a potential difference is work done on each charge, so it is also very similar to a change in energy. It's not exactly a change in energy because it's measured in volts, not joules. In fact, you learn when you look at electric field studies that potential difference is the work done on each individual charge. So it's not energy per se, it's the energy per unit charge to move that charge from a high potential to a low potential. Okay, when I say high potential to low potential, I mean an area of high potential energy, electric potential energy to low electric potential energy. All right, so when the charges are moving through the conductor, we call it an electric current. Notice electric current is indicated with a capital I. That's the symbol that we use for electric current. Now, also notice it says right here that electric current is a rate. Now, we know something about the term rate. This is a term we've looked at many times already. We've looked at velocity as a rate. We've looked at acceleration as a rate. We've looked at power as a rate. So what is electric current? It's the rate which charge travels through a conductor. So it's the rate of charge. Okay? I equals Q over T. Now, when the charge travels, just like objects, when they fall, when gravity does work on them to take them from a high gravitational potential energy to an area of low gravitational potential energy, gravity does work. Work done by gravity is the force acting over the displacement, which is the height, okay? Very similar to that, an electric potential difference also does work, electric work, to turn some other form of energy into electric potential energy. And the charges move from an area that has a larger electric potential energy to an area where it has a lower electric potential energy. Now, where can we find a potential difference? A battery can provide a potential difference. Oh, and I almost forgot. Let's take a quick look at this first. All right. Electric current is measured in coulombs of charge per second. Back in February, when we looked at electrostatics, we said charge is measured in a unit called the Coulomb, named for Charles-Augustin de Coulomb. And we know time is measured in seconds. Well, they decided to honor another scientist, André Ampère, by naming the Coulomb per second after him. So today we have amps or amperes of current. Most people just say amps, it's shorter. Where are we going to find a potential difference to create a current, to move the charges through the conductor? Like I said before, one such device is a battery, like the ones you get at the store. This shows a 6-volt lantern battery. That's one of those box-shaped batteries, not one of the little cells like a D or a C. This is a lantern battery, but it has two terminals at the top, two little curly wire terminals. One of them is the high potential, one of them is the low potential. Now, there are two thoughts on this. You see, we already know from our electrostatics that it's only electrons that can be moved from the electron cloud and passed from one atom to another. Protons can't move. We know that. They are bound to the nucleus by the strong nuclear force. However, there is a dichotomy in the science of physics as to which way we should look at charge flow. In reality, electrons move from the negative potential around towards the positive. Because they're negative, they're attracted to positive. But in the technical world, they look at it the other way. They look at which way positive charge would travel if it could. And positive charge would go from the positive terminal around to the negative terminal. The end result is the same, but there is a dichotomy as to which way it should be looked at. There are a lot of scientists who say we should actually use what's really happening, that electrons are moving from negative to positive. And there are others that say, oh, well, we've been doing it this way for so long, let's do it this way. So right now, the standard convention is from positive to negative, the direction positive charge would flow if it could. Now, I teach it this way because it's a natural intuition to realize, knowing that electrons are the only ones that move, that electrons would go from negative to positive in reality. So that's the way I teach it. And oh, there goes the clock. If we'll just hang on here for a second, it'll get through. We need to turn that thing off. There is a setting. Yeah. It's annoying. Hang on, we're going to see if we can do something about this. Thank you. All right, that won't bother us. All right, so now a battery with a chemical reaction inside, you know that one terminal is the cathode, that's the negative terminal. Cathode, hint, hint. The other terminal is the anode, the positive electrode. That's where the ions inside collect. The anions collect at the anode or positive electrode, and the cations collect at the cathode, the negative electrode. So electrons, we set up a potential difference between the terminals, okay? So then that potential difference will do work to move the electrons around if you connect them with a wire, a path to follow from the high potential to the low potential. Okay, so it's sort of like they're at the top of the hill and they're going to roll down the hill, okay, from high to low, from negative to positive. Now, in order for a current to exist, a battery is not the only thing that can provide a potential difference to do work. Any device that can provide electrons with high electric potential energy can produce a current. Such a device is called an electron pump. A battery is an example of an electron pump. Okay? Now, how do electron pumps provide electrons with a lot of electric potential energy? they convert some other form of energy into electric energy. Okay? Look at some examples here. Now, we've already looked at the battery, and from chemistry, you know that batteries produce a potential difference between the anode and the cathode by creating chemical reactions within the body of the battery. So, a battery takes chemical energy and converts it into electric potential energy, thus producing a high potential cathode and a low potential anode. Another example is a photovoltaic cell. Now, a lot of you have calculators with photovoltaic cells. That's just a fancy term for a solar cell, okay? Photo, light, voltaic, potential difference. So it's a potential difference produced by light energy. So a solar cell takes light energy and converts it to electric potential energy. Then there's also another example is a generator. A generator converts kinetic energy into electric potential energy. All right. If I had my generator here, I'd show you, but unfortunately it's in my storeroom back at school sitting on the shelf, and it's a little big anyway. So all you have to do to operate a generator is be able to crank it, okay? And you can do it by hand. You could use a bicycle to crank it. Or you could even use a little motor running on gasoline to crank a generator. A generator takes the kinetic energy and converts it into electric energy. All right. There are other kinds of electron pumps. For example, a piezoelectric cell, which uses pressure difference to create electric potential energy. And there's also a thermistor, which uses a heat temperature difference, a temperature differential to produce electric energy. Those are some examples also. Now, what is the point? Why do we even want to be able to move electrons through a conductor? Why do we want to be able to push them through? Well, easy. Electrons are what carry the electric energy that we want to use to make our appliances and our doodads run. So, we need a current to transfer electric energy to where we want to use it, whether it's to charge our cell phones, to run our hair dryers, or our TVs, or our stoves, or refrigerators and microwaves, or air conditioning. We got to have that electric energy, and the current is how we get it to where we want to use it. Now, a circuit is a closed conducting loop around which current flows to deliver electric energy to devices in the loop. So when you plug in your cell phone or your microwave or your laptop or your hairdryer, it becomes part of a circuit, a closed conducting loop. And when you turn the device on, the loop is closed and current will flow and operate the device. It will take energy to your device and make it run. All right, so we're going to get to learn to draw some symbols now. Fun, fun, fun stuff. All right, so at this point, I would pause the video and I would copy some things down. Okay, so first, I'm going to show you these symbols, and I'm going to focus in on them, and just draw a line on one part of your paper, maybe close to the right margin, just like I did, and you're going to copy these particular symbols down. These are the symbols that we're going to be using over the next few weeks to look at simple circuits. For example, you have a battery cell, and that is just a single cell. You could consider that like a C cell or a D cell, something like that, but it's a single battery cell. In a little while, I'll show you how you can draw a battery with multiple cells. Here is a switch. Switches can be open or closed. Obviously, this looks like a little knife switch. It's like a little flip thing, okay? When it's down, you get current. When it's up, you don't. We typically do show the switch in the open position the majority of the time so that it is easily visible. This funky little thing right here that looks like zigzags, that is a resistor. Later on, when we talk about resistance, I'll explain why they used a zigzag line. This symbol is a lamp or light bulb, if you will. You've got a round circle to show the glass of the bulb, and then inside is where the current's going to travel. It's going to come into the bulb, go through the filament that's inside the bulb, and then out. So that's why it looks like that. It has a little curly Q inside to represent the filament, because it's the filament that has the current going through it. Down here, these are both measuring devices. A voltmeter does exactly what it says. It measures volts of potential difference. An ammeter measures amps, although notice there's no P there. Don't put the P in, it's ammeter. Ammeters measure amps of current. So you have a circle with a V for voltmeter and an A for ammeter, okay? Now, let's look at the other side for just a minute and look at these two definitions, and then I'll let you draw the other part. There are two main parts of any circuit. There is the source. The source of the circuit contains the electron pump, whether it's a battery or the generator or the solar cell or a piezoelectric cell, whatever it is, the source contains the electron pump where the electrons get pumped up with energy like Arnold, okay? And then the other part of the circuit is where the electrons give up their energy to your devices that you want to operate. That part of the circuit is called the load. So the source gives the electrons their electric energy, and the load uses up that electric energy, okay? Now, I'm going to show you a very simple diagram, and it is very clearly labeled. You must learn now. Diagrams must be clearly labeled. That is so important. Okay, so this diagram, or schematic, if you want to be technical about it, has the two parts. This part of the circuit that I'm not covering is the source because it contains the battery. Oh, but Miss Pepitone, it's got two long lines and two short lines. Yes, it does. That's because the battery I've drawn has two single cells that are put together, okay? That's like opening up a toy and putting in two C-cell batteries. Get the idea? You always alternate between short and long lines. The long line is always the positive side. So the last line on the other side should be a short one for negative. Long positive, short negative, okay? So this battery is a 12-volt battery. That means the high potential side has a maximum of 12 volts. The low potential side is 0 volts of electric potential, okay? The current is going to start on this side and go all the way around through the circuit and end up back here, where it will have nothing left. All 12 volts of potential will have done work to go through the devices and drop off energy, and then they come back here and the electrons get pumped up again. All right? Now, let's look at the load. All right? I have put 3 devices in this load. I have a resistor here, a light bulb or lamp, and another resistor. Notice I have labeled them V1, V2, and V3 because that's the order the current goes through them. Goes through this one first, then this one, and then this one last. So V1, V2, V3. Now, look right here. I've given values to these. This resistor uses up 3 volts of the electron potential. 3 volts of work per electron are done here. So the electrons go in with 12 volts of potential from this terminal on the battery. But when they come out, 12 minus 3, they only have 9 left. So this uses up 12 volts of potential per charge. Okay? Then the electrons come around here. Now they've still got 9 volts. They go into the lamp. The filament uses up 6 volts of their potential. 9 minus 6 is 3. So when the electrons come out, they've only got 3 volts of potential left. Okay? Come around here on this side. This resistor is a 3-volt resistor. That means it's going to use up 3 volts. Well, guess what? The electrons only have 3 volts left. So they go in with 3 volts, they come out with no volts. Oh dear. So no more volts left to do any work to convert energy. So we have to go get pumped up again. Okay? Notice 3 plus 6 plus 3 is 12. We'll talk about that more in a little bit. But one thing you need to understand, 12 volts are put out, 12 volts are used up. This idea that I'm showing you, that whatever the source puts out, that and only that is what the load uses up, that's just another statement of conservation of energy. Okay? Now, a lot of times out in the technical world, you will hear these 3 devices called voltage drops. Well, it kind of makes sense if you think about it. The voltage of the electrons drops or decreases in value when they go through one of the devices. So if you see that term, don't be confused. It just tells you how much potential difference each one of those devices uses to convert electric energy back into something else. Now, so what we need to remember, though, is whatever is being used up here, it has to equal this, because energy must be conserved. If they get 12 volts of electric potential to do work for each electron, then that's what has to be used up here. No more, no less. Energy must be conserved. So this little rule right here, and it is a rule, is a statement of conservation of energy. What the source puts out, the load uses up. And it doesn't matter how many voltage drops are in the load. They must all add to the total. Conservation of energy. Okay? All right, now, not much left, I promise. Not much left. Not much left. Now let's talk about... I thought we turned that off.
We turned off the hour one.
Oh, the hour one.
Yeah.
Okay, in any case, let me go on a little further. Now, if these devices are taking potential from the electrons and using that potential to do work to convert electric energy back into other forms, for example, the light bulb does work with its 6 volts of potential to convert electric energy back into light energy, okay? That means they're developing power. Now, if you remember, when we studied power in dynamics, we said power is the rate of work done, the rate of energy converted. We just weren't talking about electric energy at the time, but it's also true for electric circuits. When a device takes electric energy, converts it back into something we want, it's developing electric power, and it's still measured in watts. Okay? Now, however, notice we don't actually have work here, and we don't have a time. So how in an electric circuit are we going to determine the power developed by any one of these devices? Well, lo and behold, there is a way to equate it. Well, we'll look at the equate in a moment. But when we're talking about an appliance that's converting electric energy into some other form, the power can be determined by taking the current and multiplying by the potential difference. This will make a lot more sense if I show you this. Look right here. Okay? Now, a moment ago, we said that current is the rate of work of charge flow, right? Okay, wonderful. But I also told you a few minutes ago that potential difference is the work done per charge. Aha! Now are you starting to see? We end up with work over time, which we know is power. So this product in electrical measurements is the same as this. Rate of work done and current times potential difference. It's still power. Okay? So I like to call it PIV. All right? PIV is electric power. PIV, PIV, PIV. We like that. All right. Now, let's take a look. If I set PIV, the IV part, equal to the mechanics definition of power, we can do an easy little thing here. Well, actually, I probably should just show you on the paper instead of rewriting it. What we do is we take the IV, set it equal to E times T. Now remember, work is also the change in energy. So if we solve for the W by multiplying the T from the denominator to the other side, we get the energy converted by a device is the current times the potential difference times the time. So whenever you want to find the energy current, you just have to get with it. Get it? Get with it. Get with it. Ha ha. Yes, I know. Bad joke. Okay. So you've got PIV for the power and with it for the energy converted, which I think is actually pretty cool. All right. Now I have an example down here, and you can stop the video if you want and work through it yourself first and then see if your answers are right. It's obviously very simple. You have a flashlight with a 3-volt battery inside, and it's producing a current of 0.4 amps. And we want to know the power delivered to the bulb. Well, with electrical terms, we have to use PIV. So you get 1.2 watts. The energy dissipated in 5.5 minutes. Oops, now wait a minute. Remember, we can't use minutes. All right? For example, current, amps of current, that's a coulomb per second. We can't mix up our time measurements. So first we convert minutes to seconds. And of course, 5.5 times 60 is going to be 330 seconds. Now, we can take the power that we just found, the 1.2 watts here, multiply by the time in seconds, and we get 396 joules of work done by the battery to convert electric energy into light energy for the bulb in the flashlight. All right, that's all from now. We've covered the first 2 pages. We've looked at some cool stuff, and we will be using it more as we go along. We do have a conference today, if today's Thursday and you're listening to this, and I think I'm going to tell you something very interesting about tomorrow's folder, so make sure that you pay attention to the conference. I don't know if you all realize this yet, but progress reports is next week. So we're going to have a discussion about what we talked about in the faculty meeting last night and the decision I've made. So pay attention tomorrow, and I think you'll be happy. All right? Talk to you later. Bye-bye.